Hello, let's look at the second lesson in Chapter 6, 6b, Complex Numbers. Let's review what a complex number is. In 6a, we introduced a complex number can be written in the form a plus bi. So here, we usually use the letter z or z to represent a complex number. In order to identify the pronunciation clearly, we call z rather than z. Z equals a plus bi, where a, b are real numbers, and I, which is the imaginary number symbol, equals the square root of -1. Or you can say I squared equals -1. In this complex number, the real part of z is a. Its notation is a equals REZ. RE are the first two letters of real. The imaginary part of z is b. The notation is b equals IMZ. IM are the first two letters of imaginary. Purely imaginary number, when your real number or your real part is 0, namely a equals 0. Let's factorize a squared minus b squared and a squared plus b squared. A squared minus b squared. This is called the difference of two squares. We can factor a squared minus b squared into a plus b times a minus b. A squared plus b squared. This is the sum of two perfect square numbers. In Math 10, we knew that this binomial is not factorable. However, with the extension from real number system to imaginary number system, or we can say complex number system, a squared plus b squared also is factorable. We can factor this one into a plus bi times a minus bi. We have already introduced how to factor a squared plus b squared in 6a already. Right now, let's look at section 3, operations with complex numbers. How can we add, subtract, multiply, divide to complex numbers? Let's look at the first addition rule. When you add two complex numbers, the first complex number is a plus bi. The second one is c plus di. When you add two complex numbers, the principle is pretty much the same as adding two polynomials, where we need to combine the like terms. A and c, they are like terms because both of them are the real parts of the complex numbers. So therefore, I combine a and c together. bi and di, they are like terms. bi plus di. When I combine the like terms, I only need to add the coefficients of these two like terms. Therefore, we can have b plus d brackets I. So when you add two complex numbers, you will have real number plus real part, imaginary part plus imaginary part I. Combining the like terms also can be applied to subtract two complex numbers. A plus bi minus bracket is c plus di. We can just apply combining the like terms. A minus c can be combined. bi minus di can be combined into b minus d brackets I. Multiply two complex numbers. Like a binomial times a binomial. How can we expand a binomial times a binomial? We apply the double distributive law, which is also called a FOIL way. We can use the FOIL way to expand a complex number times a complex number as well. We do first times first, AC. Outside times outside. That's how I got ADI, positive ADI. inside times inside plus BCI. Last times last plus BDI squared. I squared is -1. Therefore, AC with negative BD, they are like terms. We can combine these two terms. So that's how we can get the multiplication result for two complex numbers. It's AC minus BD plus imaginary part, and this is also imaginary part. So combine these two like terms. We can have AD plus BC brackets I. Let's look at how we can divide the two complex numbers. A plus BI divided by C plus DI. If you have learned pre-calculus 11, you probably still do remember. If we have a square root in the denominator, which is a binomial, we can rationalize the denominator. But here, in complex numbers, when we want to get rid of the I, just like we need to get rid of the square root when we rationalize in the denominator. Here we need to get rid of the I to make the denominator to be a real number. We multiply the top and the bottom by the bottom's conjugate. The conjugate of C plus DI is the red one, C minus DI. Therefore, I multiply this fraction, or you can say division, multiply the top and the bottom of this fraction or division by C minus DI. For the bottom, C plus DI times C minus DI, you can have C squared minus CDI plus CDI minus DI squared. The middle two terms can be cancelled out. And I squared equals -1. Therefore, negative D squared I squared will become plus D squared. And use the FOIL way to expand the top. We can combine the like terms in order to get AC plus BD plus bracket, BC minus AD close to bracket, I. So the final resulting complex number will look like AC plus BD over C squared plus D squared plus BC minus AD over C squared plus D squared I. So right now we need to apply those operation rules to add, subtract, multiply, and divide two concrete complex numbers. Let's look at how we can find Z plus W. If Z is 4 plus 3i, W is 2 minus I. 4 plus 3i plus 2 minus I. We can combine the like terms. 4 plus 2, 6. 3i can be combined with negative I. So when you combine the like terms, you just add the coefficients of these two like terms. Positive 3 plus -1, positive 2i. So the resulting complex number for the sum of these two complex numbers is 6 plus 2i. Z minus W, 4 plus 3i minus bracket, 2 minus I close to bracket. We still can apply combining the like terms to subtract these two complex numbers. 4 minus 2, 2, plus positive 3 minus -1. Negative become plus 1. Positive 3 plus 1, 4i. This is the result for subtracting these two complex numbers. Z times W, 4 plus 3i times 2 minus I. You don't need to memorize those operation rules. You can just apply the knowledge we learned in Math 9 and Math 10 to work on the multiplication. Just like multiplying two binomials, and we use the FOIL way to expand them. First times first, 4 times 2, 8. Outside times outside, minus 4i. Inside times inside, plus 6i. Last times last, minus 3i squared. I squared is -1. -3 times -1. This one will become 3. Then we combine the like terms again. 8 plus 3 is 11. -4i plus 6i is 2i. Let's look at how we can divide two complex numbers without memorizing the operation rule. But you need to know how to get rid of the I in the denominator. Z is 4 plus 3i. W is 2 minus I. To get rid of the I, that's the meaning of dividing two complex numbers. If I want to get rid of the I in the denominator, just like rationalizing the denominator, I multiply at the top and the bottom by the bottom's conjugate. The bottom's conjugate is 2 plus I. So I multiply the top and the bottom by 2 plus I. Expand the denominator, expand the numerator, respectively. The denominator can be expanded to 4 minus I squared, which is 4 plus 1. The numerator can be expanded to first times first, 8. Outside, outside. Inside, inside. Last times last. And write on -3 right away instead of 3i squared. So the result is 5 in the denominator. Combine the like terms in the numerator. We can have 5 plus 10i. If you split the fraction up into the sum of two fractions, we can have 5 divided by 5 plus 10 divided by 5i. This process is the same as dividing a binomial by a constant that you learned in Math 9. So we can simplify this division to 1 plus 2i. 1 plus 2i is the quotient result of these two complex numbers. Section 4, equality of complex numbers. Given two complex numbers, they are equal if and only if the symbol with two arrows on both sides is called if and only if. Real part equals real part. Imaginary part equals imaginary part. You can understand this one based on the knowledge you learned for polynomials. If two polynomials are equal, that means their corresponding terms must be equal. This is the same idea. Special case for two numbers are equal. So for example, a plus bi equals 0. 0 is another complex number. 0 is 0 plus 0i. A plus bi equals 0 plus 0i. That means a equals 0, b equals 0. Right now we need to apply this knowledge to help us find some missing numbers if two complex numbers are equal. This is also called the application of equality of complex numbers. Let's find real numbers x and y such that x plus yi times 3 minus I equals -i. What we can do is, let's divide both sides by 3 minus I. The left side will only give you x plus yi. The right side is -i divided by 3 minus I. We can divide these two complex numbers by multiplying the top and the bottom by the bottom's conjugate. So let's look at what is the quotient of these two complex numbers. We can expand the denominator to 9 plus 1. And the numerator can be expanded to negative 3i minus I squared. X plus yi equals 10. Negative I squared. I squared is negative 1. Negative, negative become positive. It's 1 minus 3i. Therefore, x plus yi equals 1/10 minus 3/10 I. A complex number equals a complex number if and only if x equals 1/10, y equals negative 3/10. That's how we can find out the real numbers, x and y. Of course, you can have a different way to solve for x and y. For example, you can expand the left side and then make the left side complex number equal to negative I. Then you just try to equate the corresponding terms. Here, let's look at this one. You can divide both sides by 4 minus I. But for this case, I'm not planning to apply the same method I used in A. I want to expand the left side. Using the FOIL way, we can know it's 4x minus xi plus 12i minus 3i squared will give you plus 3 equals 3 plus yi. Let's combine the like terms on the left side. We should have 4x plus 3 plus 12 minus xi equals 3 plus yi. A complex number equals a complex number if and only if real part equals real part, imaginary part equals imaginary part. Based on this evidence, we can obtain the system of two equations. Solving this system of equations is not a challenge at all, because in the first equation, you only have one unknown, which is x. 4x plus 3 equals 3. For x equals 0, we can have x equals 0. Then we sub 0 for x in the second equation. We can have 12 minus 0 equals y. Therefore, y is 12. Let's look at an example 3. Suppose a plus bi bracket squared equals negative 16 minus 30i, where a, b are real numbers and a is greater than 0. Find the possible values of a and b. How can we solve this problem? We can expand the perfect square. Let's expand the perfect square. A plus bi times a plus bi equals, this product should be equal to negative 16 minus 30i. Expand the perfect square based on the FOIL way. So we can have a squared. I want to do a little bit kind of faster in this problem solving. So the like term will have a squared and bi times bi, which will produce negative b squared. Then outside plus inside, they are the same products. I can combine them into 2abi equals negative 16 minus 30i. Based on the statement we introduced in section 4, equality of complex numbers, these two complex numbers are equal if and only if the real part, a squared minus b squared, equals the real part on the right side, and the imaginary part equals the imaginary part on the other side. Therefore, we can have the system of two equations in two variables, a and b. Let's look at how we can solve the system of two equations. We will apply substitution method. From the second equation, I can change 2ab equals negative 30 to b equals negative 15 over a. Then I will use this one to replace the b in the first equation. Therefore, I can have a squared minus negative 15 over a squared equals negative 16. A squared minus 225 over a squared equals negative 16. Multiply both sides by a squared to get rid of this denominator. We can have a to the power 4 plus 16a squared minus 225 equals 0. This is called a double quadratic. We can solve this one by using substitution. If you have very good understanding about double quadratic, you can solve this double quadratic equation right away. But you need to remember the first unknown is a squared rather than a. So I will factor this trinomial in terms of a squared first. Factor this trinomial, we can have a squared plus 25 times a squared minus 9 equals 0. So after we got a squared plus 25 times a squared minus 9 equals 0, based on the null factor theory, we know that we can have a squared plus 25 equals 0, or a squared minus 9 equals 0. Based on 6a, we should know already a squared plus 25 equals 0 doesn't produce real solutions. But in the condition of the problem, a and b must be real numbers. Therefore, this one should be rejected. Right now, we only have a squared minus 9 remain. A squared minus 9 equals 0. If we solve this quadratic equation, we can have a plus 3 times a minus 3 equals 0, which means a can be positive negative 3. There's another condition. A has to be positive. Since a is positive, we only can accept a equals positive 3, this solution, and reject another solution, negative 3. Based on a equals positive 3, what is the b value? We can use 3 to replace the a in this expression. So b equals negative 15 over 3, which is negative 5. So the possible values of a and b here, based on the conditions, are a equals 3, b equals negative 5. Section 5. Complex conjugates. Complex numbers a plus bi and a minus bi are called complex conjugates. And we have already applied the conjugate to complete dividing two complex numbers in section 3 already. If z equals a plus bi, its conjugate is a minus bi. If z equals a minus bi, its conjugate is, so we should change this one to z. Z conjugate equals a plus bi. For a quadratic equation ax squared plus bx plus c equals 0, when the discriminant is less than 0, the equation has two complex conjugates. Why? Because we can have x equals opposite b plus or minus the square root of negative delta I divided by 2a. From this notation, we can split these two solutions up by writing one as negative b plus the square root of negative delta I divided by 2a. And the other one is negative b minus the square root of negative delta I divided by 2a. We can see that this is the plus, this is the minus. These two solutions are complex conjugates. Let's apply the knowledge we just learned in section 5 in example form. Find all real quadratic equations having 1 minus 2i as a root. For a quadratic equation, ax squared plus bx plus c equals 0, if you do have one root, 1 minus 2i, you must have another root, which is the conjugate of 1 minus 2i. Therefore, 1 plus 2i is another root. Based on the 1c, the sum and the product of two roots, we can add these two roots up. So the sum of these two roots, so 1 minus 2i plus 1 plus 2i is 2. The sum of two roots equals negative b over a. The product of two roots, 1 minus 2i times 1 plus 2i, you can expand them to get 1 plus 4, which is 5. And the product of two roots is c over a. Therefore, the quadratic equation, let's get to the easiest quadratic equation first. So the simplest, the easiest quadratic equation we can have is I take the a value as 1. In this case, negative b equals 2, which means b equals negative 2. C equals 5. So the simplest or the easiest quadratic equation can be x squared minus 2x plus 5 equals 0. If we are required to find all real quadratic equations, means I just multiply quadratic equation, which is the easiest quadratic equation, by a leading coefficient, a value. So the a value can be all real numbers as long as it's not 0. Let's solve another similar problem in example 5. Find the exact values for b and c if square root of 3 plus I is a root of x squared plus bx plus c equals 0. If this quadratic equation has this one as one of the roots, the other root must be root 3 minus I. For a quadratic equation, if we have the imaginary roots for this quadratic equation, these two imaginary roots must appear as conjugates. If we want to find a b value, c value, and in this quadratic equation, the leading coefficient is 1, so we only need to look for the simplest, the easiest quadratic equation. We only need to find the sum of these two roots. We add these two roots up. The sum of these two roots is 2 root 3. The sum of these two roots should be equal to negative b over a. Right now the a value is 1. This one means the b value, or we can say negative b first, is 2 root 3. Therefore, the b value is negative 2 root 3. Let's multiply these two roots. Square root of 3 plus I times square root of 3 minus I. If you expand this binomial times this binomial, this is the difference of two squares. So let's just write down the result quickly. It's a squared minus b squared. Root 3 bracket squared minus I squared. which is 3 plus 1 equals 4. The product of two roots should be equal to C over A. A equals 1. That means C equals 4. So the B value is negative 2 root 3. The C value is 4. This quadratic equation is x squared minus 2 root 3x plus 4 equals 0. The last section is section 6, in which I want you look at the investigation in your textbook on page 181. Try to work in pairs or work individually to discover the properties of conjugates. This is the end of the lesson 6b.